I just really enjoy seeing the screen preview. Okay. Okay, so lecture 5, seasons, moon phases, tides, eclipses, and transits. We're talking about seasons, moon phases, tides, eclipses, and transits. Just pretty fast, but part of this is we've laid the groundwork for, if you never knew why we have seasons, we've laid the groundwork for figuring out why we have seasons. And then some of this stuff, phases, we'll talk about moon phases, but then we'll also talk about Venusian phases when we get to Galileo. And then tides and eclipses, I'll spend a little bit more time on, and then transits will be really important when we try to detect planets around other stars. So next Wednesday, a quiz on lectures 4 and 5. So that means 6, the second half of this class period, won't be quizzed. We'll just bundle all historical astronomy together. So just motions in the sky and sky charts, the 3 ways of pointing at stuff in this, which is quite enough material, honestly, for more than a quiz. And then we'll pick up on Wednesday with more historical astronomy, culminating in Newton's laws, and some, we'll talk about the Galileo affair and talk about why there's a schism in between science and religion. It actually has a genesis in 2 really, really prickly personalities. Okay. I read an article once that said that if you force people to choose and actually actively cogitate during lecture, they tend to remember more. So I'm trying a clicker question. So why do we have seasons? And our possibilities are Persephone ate 6 pomegranate seeds while she was in the kingdom of Hades. The Earth moves in an ellipse, getting closer to the sun in summer and farther away in winter. The Earth's 23.5-degree tilt makes the days shorter in winter, so we get less sunlight. Or the Earth's 23.5-degree tilt means that sunlight hits the Earth at a shallower angle in winter, so we get weaker sunlight. So how many people say A? What's that? It's got to be A. I don't know. There's a reason at some point, How many people say A? Come on, not even one. Fine. B, ellipse. Got some B's. Okay, C, D. So this is a pretty even split. And just since we're here, and this doesn't have anything specifically to do with astronomy, is that if you, and this might happen at some point during the quarter, if you knew absolutely nothing about a 4-option multiple choice question, what method would you use to narrow stuff down? Okay, so eliminate the ones that are just manifestly ridiculous. So now we're in BCD. What's that? Yes. Yeah, A is the only thing it could possibly be. Okay, so let's say we have B, C, and D. I try to not do this as best I can, but it's hard, yeah. You mean the sun doesn't dim and brighten and stuff like that? Yeah, so it's definitely a good thing to keep in the back of your mind. The sun isn't got a timer on it that says, let's make it winter. Oh.
Right, but I think it would more like, while it does, all the Earth does move ellipse, necessarily the tilt.
Good. Other. Yeah.
Its orbit is also just barely an ellipse. It's not nearly as exaggerated as it wants.
Mm-hmm. Good. So there are 2 things going on. One is that you guys know stuff about the Earth's orbit and tilt and stuff like that. But the other thing, there were a couple of comments that were about just solving multiple choice questions in general. One is the benevolent instructor assumption, which is something that you can usually do. I'll I hope you can get away with it in this class, is there's some stuff that was never discussed in class. So we haven't talked about ellipses yet, so it's probably not elliptical. And then secondly, there's the red herring in this is the Earth does move in an ellipse. Maybe you do know that. So just by virtue of it being a true statement, does that mean that the answer itself is true? No. So totally have true or irrelevant questions. Okay. So you can't do this in my class. I try not to let you do this. But which one has the most words in it? You think the right answer is? Okay. Secondly, these two things, they share information. And usually if you have two very similar options, there's like, kind of, they're both first order correct, one of the two is. So if I was taking a multiple choice exam in Portuguese or something like that, I would probably pick D. It shares elements with C, but it's phrased a little bit longer. Maybe I got a coin flip. Well, it turns out that it's D. So it's stronger and weaker sunlight. So this is, honestly, it's like a last resort. Obviously, first resort is fall in love with astronomy and study really hard. But it turns out to be this. But I saw like kind of a uniform distribution from B to C, so it's worth going through it. So it really is the Earth's 23.5 degree tilt means that it's hitting at a shallower angle, which makes weaker sunlight. And then in summer, it's hitting at a more direct angle, which actually makes the sunlight more intense. So more power per area. The most important thing, the most important thing by far is D. Why do I know that the most important thing by far isn't C? No, because I know something about Antarctica in December. One is that actually two things. One is that it's really, really cold. And 24-hour days. And during the 24-hour days, does Antarctica thaw and turn into a desert? 6 months of constant sunlight. So these long, long days, do they have any effect? No. So even during these long, long days, the angle that sunlight is hitting Antarctica is so shallow that it's actually really weak. So these are true. This is the most important thing, like by far. Absolutely by far. And I'll show you some pictures to, sort of like a mnemonic. Okay, so this is the position of Earth in orbit, and we're tilted towards in northern hemisphere summer. Northern hemisphere summer is southern hemisphere winter, and then we're tilted away from the sun in northern hemisphere winter, which is southern hemisphere summer. And this is not a very good picture to indicate what's going on. So I'll do this, and it might work with this lamp, might not, before showing you the really wonderfully exaggerated cartoon. Okay. So if I were to shine this light directly at the board at some brightness, and then imagine that I keep it the same distance, but then I just walk over here so that the light just hits the board with an absolutely kind of glancing blow. So what would be true about the total amount of power hitting this board? It's actually less. And if I had a nice collimated beam or something, you would be able to tell because a spotlight beam would be just this narrow circle, and then as I turn it to the side, it gets all mushed out. The beam itself gets bigger, but the flashlight is not wasting more battery power. So as you turn something to the side, it actually, the light hits at a more glancing angle, and it's weaker. There's something else going on, which is more important, and this picture is not to scale. It's really not. So it's not to scale in a couple ways. One is people aren't quite that big, and two is this an accurate depiction of the thickness of the Earth's atmosphere? It's actually like a non-snarky point, to be honest. What would be about appropriate for the thickness of the Earth's atmosphere?
Scale?
Yeah. Is it? Yeah. I mean, a couple millimeters. So most of the gas that surrounds planet Earth would be within that black line. So we'd be crushed. So we'll talk about this. So the Jovian atmospheres, you can, if you dropped like a lump of coal into Jupiter, it would be a diamond by the time it dropped, towards anything that could resemble a surface. So all of the weight of this air on top of That's why on this bizarro Earth, these people evolved to be so big and powerful. The weight of all that air would just crush you. Yeah. Mm-hmm.
But are a lot denser.
You mean it would have to do with the structure of the alien that looks a lot like a human themselves. So you'd have to just structurally withstand all of the weight of air on top of you.
Oh, not the people.
So the planet itself, I think, would be okay because this is, fluffy gas, and the center of the planet is, about 10 to the 24th kilograms of iron and nickel, and that's pretty hard to crush. Oh yeah, the humans, little squishy humans. Yeah, not the planet itself. So you can crush iron, but you have to wait for supergiant stars and supernova to get to that point. But so this is like all pictures in astronomy. Unless it's an actual picture, it's probably not to scale. But what it does depict and exaggerate the effect of is this. And this is just, it just happens to be summer in the northern hemisphere. And look at how much atmosphere this light has to make it through to hit the surface. This much. As I move up to, the Arctic Circle, especially that guy, who even still, it's 24-hour day above the Arctic Circle, light's shining for 24 hours. Look at how much path length that light has to make it through to hit that person. It's much longer. So even though the scales themselves are exaggerated, the multiple, like 3 times longer, 4 times longer, is correct. So here it would take 4 times more, sunlight has to pass through 4 times as much atmosphere, and it gets scattered, and it gets absorbed and attenuated, and it's much weaker. So this is by far the overriding reason. So it's the actual angle of the light. And this idea, I don't know if people are like history buffs, gets forgotten and rediscovered over and over. If you take a cinder block and you try to shoot a bullet through it, it's got to travel through some distance. If you just tilt the cinder block, you realize that the apparent distance it's got to travel through is much farther. And so, Leonardo da Vinci did this, clever guy, and then the Soviet Union did that in 1934, and everybody else was doing this, making these designs with flat walls, and they rediscovered this ancient principle, sloped armor. But really it's that. It's like we're tilted away and the light has to travel through a greater path. And you actually notice this on a daily basis. Do you get sunburned at noon? Theoretically, if you live someplace where there was sun. Get sunburned at 4 p.m. if you go out sunbathing? I know you know this answer. Yeah, so probably not. So it would take a lot longer. And that's just because as we're rotating on our daily rotation, now the sun is towards the edge of the horizon, and it also has to pass through more atmosphere. So you see the sun looks dimmer. Don't look at the sun, but if you were to, you would do it right at sunset. So same idea. So this is it. Okay, so I'm going to show these, and they're linked off of the notes in the classroom. This is the whole scheme together, and this shows, again, a comically exaggerated person, the orbit of Earth with its tilt. So now it's spring, we're tilted to the side, and now it's summer, summer in the northern hemisphere, we're starting to be tilted towards. And then down in this panel, you see the rays of light as they hit the Earth. And so right directly straight down overhead, if we were to paint on an atmosphere here, the atmosphere itself would be absorbing and scattering and attenuating more and more light as it comes in at a shallower angle. So kind of sloped armor effect. Okay. Yeah, we put the guy at the equator. I forget which panel we can switch. Haha. So we can go to above and you can see these angles. So the guy is not to scale, but the depiction itself of those angles is correct. So no sunlight, and it'll take us a little while. Maybe we can, I don't know if we can speed this one up. So look at how shallow the light comes in when light returns to the Arctic Circle. Incredibly shallow and incredibly weak. And then even though it's light for 24 hours a day at this point, still, this is about what you're getting at 6 p.m. at Seattle latitudes, basically. So most important thing, absolutely most important. Slow. This is the. Yeah, this is just kind of cute, so I'll run it once. Somebody just took pictures over the course of 365 days in the courtyard. So this is the campus of the University of Nebraska-Lincoln, where they made all these really nice animations. And you can see the same thing as the correlation of snow. So one picture every day at noon, one picture every day at noon. And you can see the correlation in between leaves falling off trees and what you traditionally associate with seasons, and this lengthening of the shadow. The shadow is not getting longer and shorter because it's later earlier in the day. It's just because it's earlier in the year and later in the year. So it'll get really long in December, and then you'll see snow. This is a place that actually has snow. Okay. So secondary reason, it is a reason. I mean, if you have 12 hours of sunlight versus 24 hours of sunlight, obviously you're receiving twice as much energy, all other things being equal. But again, how do I know that this long day, short day effect is not the most important thing? So this is why it's pretty close to the equator. It's not right on the equator. And then there's Antarctica that's down here in December, for instance, 24-hour days. So do you see people in bikinis at the South Pole? And 12-hour days. Do you see people snowboarding in Hawaii? Yes, actually. So these are all astronomers. If you want to lose your mind and go to the South Pole and work on a crazy experiment, this is what ends up happening to you. They actually ration alcohol during the winter. But it is the second most important effect. And this one, this is actually Hawaii, but this is 4,000 feet above sea level at the Mauna Kea Observatory, which you can see in the background. So that is literally the South Pole. But okay. So any questions about that? Yeah. Yeah. So the question is, why do sunsets and sunrises have different colors? Is as well as just attenuating and eating some of the light, it also scatters it. So what you get is kind of a prismatic effect. Like if you shine white light through a prism and it spreads all the things out. The atmosphere is actually a reasonably good prism, to be honest, because you do notice this kind of rainbow effect for a really clear day, sunset or sunrise. And if you're really lucky, there's a thing called the green flash, where if you're looking at sunset over a totally uninterrupted horizon, there's a moment where, so it goes from blue when it's daytime and then it's red at night. Well, where's green? There's not a lot of green in the in the solar spectrum, but for one brief moment, you see this band of green appear. So it actually acts just like a prism does. Yeah. No, it's a real thing. I know. I love busting on movies, but the green flash stuff is actually true. Yeah. You have to be pretty lucky to see it. Okay. So how does this? So that's just scientific literacy, what's going on Earth. But then the other questions we're going to ask, and these are kind of legitimate questions because we'd like to know stuff about exoplanets and how to find them, and what would happen if I lived on one. Kind of a sci-fi question, but legitimate physical questions about not our own planet. So these are two of the outer planets, and Uranus is tilted with respect to its orbital plane around the sun by about 90 degrees. What do you think the seasons would be like? So I think the year on this planet is 84 Earth years. It takes 84 Earth years to go around, if I remember correctly. So how would you characterize the seasons? Is that? For a while, but then what? Yeah, you just got to wait 40 years, and then you get endless summer, right? So really what's going on is these things are orbiting in a plane like this, and the sun would be somewhere over there. So this is the plane in which the sun is, and you can tell the rings. I chose these planets because the rings kind of give it away. Is that for half of its orbit, this planet is just facing, or the northern hemisphere is just facing the sun, and the southern hemisphere is just facing away. And for the other half of the orbit, they switch, basically. So you really get like 40 years of constant day and 40 years of constant night. Just to kind of, they're really far away, so these seasons aren't overall like, as strong as you might see on Earth. So the word that we'll use is extreme, and that just means like extreme variation, is that it's really obvious what summer is and it's really obvious what winter is. So for instance, during summer, I can see the sun from Uranus, and from winter, I can't for 40 years. That's kind of a bummer. So you would just say the axial tilt of the planet is 90 degrees. There is a specific question about what happened to this planet, because you wouldn't expect, actually, and we'll get into this when we talk about the formation of the solar system, is like you would actually expect everything to be spinning flat in the plane of the Milky Way galaxy, or sorry, the plane of the orbit. So imagine that you had like a bunch of tops that you spun on a pizza dish or something like that. You'd expect them to be spinning the same way that they were moving. And the fact that this one's sideways there's a mystery there, actually. Yeah. There's no special name for it. I mean, extreme seasons, maybe. Yeah. So you could have totally pathologically, and that would be a question unto itself, is you could have had a planet that has a ring system that looks like this, but it's spinning like that. Don't ask me how you would do it, but I know you can get there. There's nothing wrong with the physics of that. So that in and of itself, so this, we know that it's spinning this way because literally we've sent a machine out and looked at it, and we've seen weather patterns circulating this way. And it's possible before then maybe some radio astronomers looked at it and saw that it was beaming like aurora borealis type stuff off of that, those axes. But it's, I'm sure that most of the time you're right. But totally weirdly pathologically, you could have some like ring of debris like this, and the planet might be spinning like that, I guess. And you're not breaking any laws of physics by doing it. It's not the case. So really, when I said that, I just meant just to guide your eyes. This is the way that it's spinning, and that's the axis. So something orbiting, plunging into and out of the plane of the ecliptic. Yeah, long period comets do that, and they're also kind of a mystery. Is why are these? Everything else is basically orbiting in the same plane. Why are these comets just dive bombing us? Yeah, I'm sure it's probably some really exotic comet. Okay. And then, other questions? Just the ones we made. So Earth does have satellites that orbit in funny ways, but we made them. So we really only have the one major satellite, and it's 5 degrees tilted. So our axis is like this, we'll just call it like that, and the moon is orbiting us off at like a 5-degree tilt. Remember that fact for 20 minutes. Okay, and then how would you characterize the seasons on Jupiter? So Jupiter basically has 0-degree axial tilt with respect to the plane of its orbit. So the sun's here, the orbit's there, not tilted at all. So would you be able to discern seasons at all of any type on Jupiter? No, just the day, just the terrible, terrible 10-hour day or whatever it is. It's a pretty big statement, right? So that thing spins once every 10 hours. Good. So we'll ask questions like this when we get to our trove of 2,400 exoplanets. Okay, so moon phases we won't talk a lot about because I want you guys to draw and sketch the geometry yourselves and then generalize it to phases of Venus, which is a really, really, really important set of observations that Galileo made. But I'll just say that, in a week we'll do this and you don't have to wear weird bright blue culottes. But there is something else going on in the moon that we will talk about, and it has something to do with just stuff that's going on Earth, but it also has to do with a lot of other processes out in the universe. So anytime you get two bodies interacting pretty closely, you might have to deal with this sort of stuff. what is the moon doing? So there's a bunch of pictures over the course of a month that's very, very, very shady. Yeah, and it orbits us once every 28 days, so if it's always facing us the same direction, what is it really doing? And does it make you sort of uncomfortable, like the moon's got something to hide? So imagine that like the video camera is the Earth and I'm orbiting it and I'm the moon. It's kind of like I'm doing this, right? It's not suspicious behavior. So the way that you might describe that is what's true about the lunar day versus the lunar year, quote unquote. So that is to say the time it takes the moon to orbit the Earth once versus the time it takes the moon to spin once on its axis. So if the day was longer, it would like turn a little bit every time. So if it's orbiting us once every 28 days, how long does it take to actually execute like a full rotation on its axis? So it's got to be the exact same period of time. So sorry to bring this poorly dressed person into stuff again, but so if, I think so, yeah, with bowling shoes. So if the lunar day was infinitely long, the moon didn't spin on its axis, what would happen is we'd see the front of the moon, and then 2 weeks later we'd see the back of the moon. Because we always see the same face, what's happening is, again, this kind of sneaky business where the moon is rotating once, making a full circle, once every 28 days. And over the course of your lifetime, over the course of recorded human history, has that ever not been the case? You ever read something where people are like, yeah, we saw it was when the moon was turned with the backside facing us. So this has always been true for as far as, at least recorded human history. So for 6,000 years, this is such a precise agreement in between the rate of lunar rotation and the rate of lunar orbit that something must be going on. Obviously, Illuminati aliens living in a hollow base, right? No. I think so. So what is this? So what caused this? Is that? So this is tidal locking. And it's the exact same phenomenon that causes stuff like this. So this is like a really nice example of tides on Earth. This is some UNESCO World Heritage Site in Normandy in northern France, and during high tide there's like a little causeway and you can drive out. There's a lower parking lot there that you should not drive to right before high tide and leave your car parked or get transfixed by the cathedral, because this does flood. And during low tide, you can go out and whatever, there are grasses and land that is exposed. And so people understand this motion enough that it's very regular. Things, rise and set over the course of 12 hours up, 12 hours down. So these are tides, right? We understand tides, or at least know they exist. What's that? Yeah, there's something funny going on where it's like salt water. I don't quite know why there's vegetation there. I think about that every time I see this slide. It's weird. Okay. So this is what tides are, is that the moon this actually isn't wildly out of scale. It's a little bit out of scale. The moon should be maybe twice as far away. But the moon is close to us. The reason the moon is orbiting us is we're exerting a gravitational pull on the moon. The moon also is exerting a gravitational pull on us. And that gravitational pull depends on how close it is. So we'll get there at the end of next week, but all matter is pulling all other matter in the universe with gravity, but that gravity depends on how close you are. So the 200 or 150 billion stars in the Andromeda Galaxy, we do not care about their gravity because they're really far away. Something interesting happens when you get things pretty close is the force of gravity depends on not only where you are, but the size of the object. So imagine that the moon is pulling on the Earth, and this part of Earth is a little bit closer, and this part of Earth is a little bit farther away. So this part of Earth gets a little bit more of a gravitational tug. This part of the Earth gets a little bit less of a gravitational tug. And overall, what it does is it kind of deforms the Earth a little bit. It stretches it like an accordion. And we notice this pretty, obviously because we're surrounded by water. So in the oceans, you can really easily deform the oceans, high tide, low tide, as the Earth spins underneath this. So really, it's always kind of egg-shaped like this, but as we spin by, you just happen to be here in high tide region, low tide region, high tide region. So you get 2 a day, 12 hours apart. Are we doing the same thing to the moon? Sure, right? We'll get there, but there's nothing special about gravity, like, mass pulls mass. So here's some mass, there's some mass. Yeah, so what would happen if the moon was rotating on its axis is the question, and that's a great question. That was exactly the thing I was going to ask you guys. So what would happen if the moon was rotating on its axis? It would be the same thing, right? So there would be tides, but the moon just doesn't have an ocean, so we wouldn't really notice it necessarily, but there would be this accordion-like stretching of the moon, and as the moon spun underneath that stretching, what would really be happening? Sort of like grinding rocks and tectonic plates and stresses and friction, right? So we don't care because we're a lot of mass compared to the moon, and water is, pretty easy to deform. But this constant rising and swelling of tides and us spinning underneath it actually is causing friction. So to do this, you are kind of warming up the Earth, and you're stretching it and squeezing it like an accordion. And the day actually used to be a lot shorter than it is now. So go back, 2 billion years, and we had a 14-hour day on planet Earth. Because slowly the moon is kind of slowing us down through this constant friction of tidal forces. So we're doing the exact same thing to the moon, except we won. And what does winning mean when you exert these tides and these friction? So we stopped the moon. The moon used to be spinning, especially just after it formed. And over the course of, maybe could have been less than 1 billion years. I don't know the number offhand. We basically stopped it, so it's always facing us, same face always. So, and we did a really good job because you've always seen the same face of the moon for find any historical document, you'll see like the craters are still in the same spot for the last 6,000 years. So this is what's called tidal locking, and I think this might be a little bit of an exaggeration. It may have taken less than 1 billion years. And this is a little bit exaggerated because it really looks like we're deforming the moon really far apart. So this is the only configuration where we're not like making the moon work like an accordion and stretching it and shrinking it, as if it's deformed once and then it just kind of keeps in the same shape orbiting us. Okay. Does that make sense? Okay. This is going to be a pretty generic thing. Io, the moon of Jupiter, is smaller than our moon, and Jupiter is bigger than us, Earth. Do you think that there's some tidal locking kind of mechanism going on with Io? Probably. So keep that in the back of your mind. But this happens a lot, so a lot of things are tidally locked. And it's really just tidal, the frictions. And secondly, if you drop your friend into a black hole, tidal forces will be important there. The supermoon thing, as far as I can remember it, is the confluence of a couple of things. One, you have to have a full moon, which is just the phase, and that varies over 28 days and achieves a maximum, whenever. And then secondly, the orbit is not quite a circle, it's slightly elliptical. So sometimes the moon is closer, sometimes the moon is farther away. And if you manage to get them both to line up, where you have a full moon at the closest part of its elliptical orbit, then it appears really bright and really big. I think that those are the only two effects in a supermoon. But yeah. So the ellipticity of the orbit is not particularly incredible. It's not like a comet that's whizzing in and out. But yeah, good. Other questions? Okay. So eclipses. We'll talk about general alignments of things. Any three celestial bodies, if they happen to line up, it's a great Scrabble word. I don't even know if there are enough Z's. It's called syzygy. Specifically, Earth, Sun, and Moon, that's an eclipse. There are only two ways of doing this. So the only two ways of having the Earth, Sun, and Moon in a line are what and what? Well, it's written right there. But what does it mean? So sun, earth, moon is okay, and sun, moon, earth is okay. Earth, sun, moon would be terrible. So there are only two ways of doing this, and they each get their own name. In fact, eclipses in general have a three-word description. One is eclipse. So if somebody says eclipse, you know that there's moon, earth, and sun in a line, in a perfect line. And some aspect of one's shadow is cast on the other. The second word is the thing that's getting eclipsed. So the thing that's being made invisible is word number two. So solar eclipse would be we can't see the sun, which means the moon gets in between the earth and the sun to block out the sun. Lunar eclipse means the earth gets in between the moon and the sun, so we can't see the moon, which usually you can, actually. So the third word will have to do with the quality of the shadow itself. But before we get to that I chose this on purpose. I think this is the worst picture that you'll ever be exposed to in this class. This terrible, terrible picture, as well as being freakishly not to scale, there's something else wrong with it. And if I were to look at this and take it very seriously, I would say, like, well, why don't we have a solar eclipse every 2 weeks and then a lunar eclipse 2 weeks later? Because when I peer at this, I've got, sun, moon, earth. Looks like somebody standing here wouldn't be able to see the sun because the shadow of the moon's basically right on top of them. So solar eclipse. And here, if I'm standing on earth, the shadow of the earth is blotting out the moon, so I should see a lunar eclipse. And according to this picture, I know that this is a month-long orbit, so why doesn't it take a month? Every month, 2 eclipses. That would be really great. Why not? So the Earth rotating, and that would just potentially mean that you had to go to a different place to chase it down, but there's something else going on there. So the tilt versus axis, that would also mean that maybe I would have to run and chase it down somewhere else. But somewhere on Earth. So now, some orbital tilts become important. So in fact, I see 2 orbits on this flat 2D screen that I cannot make 3-dimensional unless I took a razor blade to it, which I'd probably get in trouble for. All of this is compressed onto 2D. And if this were really true, and I just, chose this screen to be the orbit of Earth around the sun, and it was also true that the orbit of the moon around the Earth lie on the same plane, then this would definitely happen. I might have to run around and try to find it, but there would be a lunar eclipse, solar eclipse once every 2 weeks. What must be true, because I know that that's not happening? So what needs to be true about these 2 orbits? They're absolutely not. So they're actually tilted. And, if this really is the orbit of Earth around the sun, this thing needs to be tilted out of the screen and into the screen. So now we have a third way where astronomy pictures can be really misleading. So not only are these sizes and distances horrendous, and, Earth isn't really that color, the sun should be a lot brighter than that, but this orbital plane should be tilted. And if you are following along in the textbook, I'll show you the really weird picture, which I think is actually kind of cute that they used to illustrate this. So it's 5 degrees, and it's a really important 5 degrees, because these things are far enough apart that 5 degrees is enough for the shadows to miss each other a lot. So tilted slightly, which means that maybe the moon is here, and the moon's shadow actually misses Earth when they would be in a line, or maybe the moon is here and the Earth's shadow misses it when they would be in a line. So there needs to be some sort of tilt, and the moon gets out of the way. And this little 5 degrees, so 5 degrees tilted above the ecliptic, which is our orbit around the sun, is enough to make sure that we don't have 2 eclipses every month. This is the textbook picture of it, which might indicate that we live in a giant bath or something like that. But they're just trying to depict exactly that effect. So these are the places where you can get an eclipse and you can't get an eclipse. And just the idea of the water, the representation of the water is just so where flat is. So the bath water is the ecliptic. And this is still, of course, terribly not to scale. But here you see the underwater moon casts its shadow kind of like below Earth, so Earth doesn't intersect with it. And the above the water moon is out of the way of Earth's shadow. And this happens most of the time. To get an eclipse, what you need to do is you need to be pretty fortunate. You need to have the moon splashing down into the water of the ecliptic in this sort of picture right as it's in line during, the couple of hours of its month when it would be perfectly aligned. And then here, actually this would be less, since that's a solar eclipse, that would be about, a couple of hours, I guess is right. And here, the lunar eclipse, just as it's splashing down, and it happens to be in a line. So this is, I don't know. It's sort of cheesy, but it's sort of helpful. And this is the whole thing in real scales, actually. So this is the real size of the moon and the Earth relative to each other and the real distance. And you can depict that. People in the back probably have to squint a little bit, but I'll just tell you it's like 2 pixels across. And then this is what you would or wouldn't see. So most of the time, they miss. And you can predict them if you're pretty good at this, and there's so-called eclipse season. So whiff, don't even see it. And we'll zip a little bit faster. And slow down for eclipse season. Okay, so now we're starting to get closer, and you see now the near misses are even more near misses. So that might have been a partial lunar eclipse. And looks like we're about to get one there. Okay. So 5 degrees means a lot. Remember these very far separated distances. Okay, same picture, basically. Okay. So the third term when you're characterizing eclipses has to do with the fact that it's not enough just to say shadow. So shadows actually have parts. If anybody's taken like an illustration or still life drawing class, you probably know this. But because the sun itself has a finite size, it actually casts a sort of chunky shadow. And there's the part of the shadow that's total. And then there's a part of the shadow that's partial. And they come with their Latin names, and I'll show you guys in a second. So the so-called umbra, which means shadow in Latin. I don't know why they just didn't change it to shadow. And the penumbra, which means almost shadow in Latin. And this actually becomes important because the penumbra and the umbra, especially for lunar eclipses, are each big enough to hide the moon. And it depends on where you're living. Maybe you get a better or worse eclipse. Yeah. Yeah, so not here. So the question is there a point in the middle of the shadow that's actually light? And it's absolutely true. So this was, it's this thing called it's actually got a couple of names, but we'll call it the Arago spot because that's the person who actually saw it. So the idea was when people were arguing about whether or not light was a particle or a wave, if light was a particle, it would just be like, imagine that the sun's firing bullets at this target, and obviously there would be no bullets hitting there because it's in the shadow of that. If light was a wave, it would diffract like waves do, and if you actually work out the math, there should be a point of maximum interference at the center of this, and a bright spot. And this guy Poisson, who didn't believe in the wave theory of light, said like, oh yeah, well if light was waves, there should be a bright spot at the center of a uniform disk illuminated by monochromatic light. And then they went and they looked and they found it, actually. So it was very ineffective trolling of the theory. But this is for like, if you want to see the Arago spot, you've got to have a well-made disk and a laser, and none of this is going on, so it's a total mess. But yeah, that's absolutely correct physics. It's just this is a very bad experiment if you want to see the Arago spot. It's not a wavelength thing. It's the fact that the sun emits a tremendous amount of different wavelengths of light. It's not uniformly circular. It's not coherent is the most important thing, is that the light coming from here and the light coming from there, they're not being emitted in phase and sync with each other, whereas a laser it would be. So it's actually pretty impressive that Arago did what, I don't know, she or he did. So I think you'd have to like punch a little hole in a wall and then really carefully engineer this. It's not easy, actually. So it's not. But yeah, it's definitely a thing, but that would be a huge and difficult experiment. Okay, so let me actually go back to this all black slide I had. Actually, let's just turn this off for a second. What's that? Yeah, I think it was, so Poisson definitely was. He just happened to have the wrong idea about light and shadows. And my understanding of the story is it was almost like instantaneous, like he almost like snapped it out like a retort. You know, like if light is a wave, well, you would definitely see a bright spot at the center of a shadow. And then people went out and looked and said, like, yeah, we do. Thanks for the suggestion. Okay, so this is, and people in the front see this a little bit better, is you don't really notice umbra penumbra over the course of typical life because the conditions for a really, really big penumbra are that you need to be far away. So as you see my shadow kind of blurring out, do you see like the kind of crappy partial shadow and the total shadow? And secondly, this thing needs to be finite. So when we finally burn out our last incandescent bulb and I go to LEDs, this would not work at all. So mostly, you know, you're close or the light bulb is small, you're used to seeing umbra, but you can kind of engineer some situations where you actually see this hazy edge of penumbra. Now imagine that that's the size of the sun and this is separated by, you know, almost 400,000 kilometers. Now you get a pretty substantial penumbra and umbra, and they actually treat eclipses differently. Okay. So really important for the lunar eclipses, a little bit less so much for the solar. Is it making noise? Question is it making good noise? Okay, so I'll see it, and you guys try to visualize it in your mind until the projector warms up. So first, let's talk about lunar eclipses. Great. There are three possibilities. So lunar eclipse means what's the thing I can't see? Moon, which means the moon is in the Earth's shadow. And it could have two possibilities in the marginal case. Is you could stuff the moon inside the penumbra or the umbra. If it's in the penumbra, it has the very obvious name of a penumbral lunar eclipse. If it's in the umbra, we just kind of get sick of Latin and call it a total lunar eclipse. These actually happen pretty frequently. They're really like, maybe they're worth getting out of bed for, but they're certainly not worth like traveling for. Total lunar eclipse, I think we had one last summer in Seattle. They're actually pretty neat and extreme, so you see them. Awesome. Yeah, totally. Was that on your phone? It's almost weird. They're getting pretty good. And then the middle case is that you can actually be halfway through the umbra, in which case it's called a partial lunar eclipse. But you are still in the shadow. The entire moon is in the shadow. It's just half penumbra or some portion penumbra, some portion umbra. So somebody said any of these three-word terms, would you be able to sketch the diagram of Earth, Moon, Sun, and then draw the shadows? Awesome. If not now, then by next Wednesday. And here's a picture of the whole thing. So this is actually I think this is a total lunar eclipse, but they just didn't really show the total part. And you can see the start of the shadow creeping across. This entire part is in the penumbral shadow, and this is the umbra creeping across. And I think the exposure of the film has changed there. So much darker, but it looks blood red. And then finally creeps across again. All of the stuff that looks bright is actually still in the penumbral shadow. This takes hours. It's nice, very leisurely. Okay. So we're going to we'll just start talking about it in terms of solar eclipses, and we'll talk about why, but we're really good at predicting these things because, again, for now we can just say that the motions of celestial bodies are really good timepieces, and all you really have to know is the past behavior, and you can predict the future behavior. You do this in a very sort of pedestrian way when you're like, I will go to such and such a location in August because the weather will be great. So you're using, you are using celestial motions as a sort of timepiece and their regularity. You can do that including their alignments. So these are the paths of total solar eclipses, not lunar. So the lunar ones are so frequent. People really care about this. I will point out that on August 21st, 2017, through northern Oregon during the day, the path of totality of a solar eclipse will happen. And this is an old picture too, so this goes all the way into 2025. So they're telling you that in 2025, go exactly wherever it is. Oh yeah, so you got to go to northern Greenland and then hang out there, and on March 20th, 6 a.m. or whatever it happens to be, the path of totality of the solar eclipse will pass you. Would you trust people who said that? How much do you trust astronomy as a timepiece? Yeah, we'll see. I don't know. What if somebody showed you this? And these are eclipses in between basically 600 and 580 BC. And this is where they were. And we could put times on them too. So this is legitimate. This is very trustworthy. People absolutely believe that this is where an eclipse happened in 585 BC. And there are two stories about this eclipse in 585 BC, one much more entertaining than the other one. So one is that this is actually referred to as I think Isaac Asimov called this the oldest precisely dated historical event. The Battle of Halys, which is this river that goes through central Turkey, May 28th, 585 BC, late afternoon. I don't know if I actually remember the story correctly, but are these two groups of people at war, the Lydians and the Medes. I think that the Medes king employed some hunters from some other group, and they came back empty-handed, so he insulted them, so they killed and cooked his son and fed them to him without his knowledge. And then they ran away, and the Lydians harbored them because they hated the Medes, and then they went to war for 6 years over that. And on this sort of culminating day when they were all gathering to slaughter each other on some particular day, a big dragon came and ate the sun, and they all freaked out, dropped their weapons, and made peace. And in true, Iron Age fashion, the king of the Lydians gave his daughter to the, this is how things were settled back then. It's horrifying.
Right.
Yeah. That's the boring story. The really interesting story is that a Greek, we were really like astronomers back then, but a Greek smart guy, philosopher, whatever you call him, predicted that this would happen. So as far as we know, this is the earliest predicted eclipse too. So this guy Halys said an eclipse will happen on such and such a day based on his knowledge of the precise workings of the cosmos and using astronomy as a timepiece. And nobody exactly knows how he did it. Eclipses tend to occur in pairs, but he correctly predicted it. And I think so. I think you get away with it here, but I definitely know of circumstances, especially in there are Chinese astronomers that were beheaded for not correctly predicting eclipses. So eclipse happens, and then the emperor says, hey, why didn't you tell me about that? And so I don't know if his life was at stake, but I think he was pretty excited. I would have been. I don't know. I predict eclipses by checking the internet. So good. It's really good timepiece. And we understand, and we'll talk about why we understand, but we understand the motions of celestial bodies exceptionally well. Okay, so the other flip side of this, and these are really cool, actually. If you ever have a chance to see one, you should. Anybody actually ever seen a total solar eclipse? Once? Yeah. When the Earth gets in the way as it spins. So same thing, except slightly different terminology is, now we're talking about the moon's shadow being cast on the Earth. The moon's shadow has a penumbra and an umbra. And this has nothing to do with where the moon is necessarily. It really has to do with where you are on planet Earth. So if you happen to be standing in the moon's total shadow, the umbra, you're observing a total solar eclipse. So that. If you happen to be standing in the moon's penumbra, you are observing a partial solar eclipse. You don't really think about it as I'm standing in the moon's penumbra, obviously. You think about it as saying the dragon ate half of the moon and didn't finish its meal. One of these happened in Seattle a couple of years ago, so you could actually see it with special glasses, of course. And then there's this. So this is a total annular solar eclipse. And it looks as though it should be a total solar eclipse. It looks like the moon totally goes across the path, like perfect trajectory, lines up as best as it can in front of the sun. But there's actually a ring of fire left around the edge. And sometimes you see this ring of fire and this annulus, Latin for ring, and sometimes you don't. So any guesses about what on Earth could possibly, or what in space could possibly be going on? Yeah, a little flare-up of solar weather. That's a really good guess. The moon somehow reflects and bends it. That absolutely happens. I don't know. I should have mentioned this, but you can actually see that effect. See this hazy ring right there? I don't know if everybody can see it. That's scattering through the Earth's atmosphere. So it's got a funny shadow. The moon's atmosphere is not so great. So those are all good suggestions, but it's not exactly right. So this has to do with the elliptical orbit of the moon. Sometimes the moon is closer, sometimes the moon is farther away. And so there's absolutely no coincidence in the 28-hour day of the moon. That was physics. It is actually a coincidence that the apparent size of the moon and the apparent size of the sun are basically equal, like total shit luck. That it looks like, hold a quarter at arm's length and it covers the light bulb exactly kind of thing. It's just completely random luck that the apparent size of the moon just covers the sun. And sometimes it doesn't quite work out that way because sometimes the moon's a little bit farther, so it appears a little bit smaller. Sometimes it's a little bit closer, so it appears a little bit bigger. When the moon is farther away in its slightly elliptical orbit, it actually leaves behind the little ring of fire, the annulus. So, or you happen to be a little bit farther away on Earth. So if you were here, you'd be farther away than if you were there. So you can also get an annular solar eclipse. And I don't know which one would be cooler, but they're both pretty impressive. Okay. It's the fact that the moon, depending on either where you're standing on Earth or where the moon is in its elliptical orbit, is either closer or farther. So if I wanted to blot out a light or something like that, and I put my thumb up really far away from my face, it covers less area, but then if I do this, I can cover more area. So it's the same thing. So when you and the moon are closer, it'll cover more sun. Oh, it's just because this is a little bit too small to cover the whole thing. So the lid's too small for the jar.
Kind of bleeding. It seems like solar less than some covered.
Yeah, I don't even know if they're real photos, but what they're actually, the exposure on the total solar eclipse one must be way off. So I think they're cranking up the exposure or something like that. But you are seeing space weather, so that's what's called the corona. I don't even know if these are real pictures. They're so pixelated and grainy. But yeah, you're absolutely right, is that there must be some effect. You should see more light in an annular solar eclipse when you look at the sun, which you shouldn't do. So the last question is, why are we so excited about solar eclipses and so not necessarily excited about lunar eclipses? So why do the lunar eclipses happen so much more frequently? Who's got a bigger shadow? Yeah. So it's much easier to fit the moon in Earth's shadow. And that happens really frequently compared to having the pencil-thin umbral shadow of the moon etch its way across Earth. And the other thing is everybody on Earth can see when the moon is in the Earth's shadow. You have to be at like the specific location to see the sun being covered by the moon. So much, much more frequent lunar eclipses. Not saying they're not like really pretty and cool, but it's just a total solar eclipse is definitely an event. Okay. So we'll stop and actually watch one. This is my first chance to have random British narration in this class, which I can't get enough of. Everything's better with a British narrator, actually. Just tell you complete nonsense and you believe them. So this is a fairly recent total solar eclipse that happened, and a path of totality went through a pretty major city, at least like importance-wise, so Varanasi in central India, I guess. And right through the heart of the city, I don't know if we have... What's that? That's so could be that's I think somebody left these plugged in. Maybe that's it.
By low cloud.
Is there a question? Yeah. Yeah. Yeah, he does a lot of... I think he's like a particle physicist. But BBC just kind of horned him into doing all this stuff. He gets excited, so it's nice.
See the disk of the sun at the moment, it's obscured by low cloud. The edge of the moon is at this point just beginning.
Can everybody hear that? Ish?
See the sun emerging through the clouds. See the disk. Oh, you can see the moon. Can you see the moon on the top? Oh yeah. See the limb of the moon there, absolutely fantastic. Yeah, see it. You can see that the celestial mechanics, the clockwork of the solar system work. The alignment is absolutely perfect.
They don't actually make that music when they happen. Sun with other balls of rock, then look at that. That's the solar system coming down and grabbing you by the throat. He gets excited. Okay. Okay, so just to generalize this a little bit, and if you understand these, then there's a lot of stuff that you get for free. Because the same thing's happening everywhere. So there are asteroids that are going in front of stars at any given moment, and planets going in front of their host stars and maybe dip a little bit of their light. eclipses are just sun, earth, moon. But the same idea, even among the other bodies in our solar system, this is a transit. So transit would be a planet crossing the disk of the sun. So this is the transit of Venus that occurred a couple of years ago and was also more or less visible from Seattle-ish area if you could get away from the clouds. And this happens over the course of hours and hours. So you would, if you took a picture of the sun under safe circumstances, you would see this dot crossing across it. And there's a transit of Mercury, I think that happens a bit more frequently. So the next transit of Venus will occur in 117 years or so. So wait for it. And again, any three celestial bodies that happen to align, just got another term. I'll never ask you about it, but it's great if you ever want to cheat and win at Scrabble. It's a syzygy. What do you suppose happens if I were to just sit there and collect the total amount of light coming from the sun during a transit? So Venus doesn't look that big, right? But it is definitely blocking out some of the light. How much do you think? 10%, 1/100%, somewhere in the middle? More, less? 21? 0.1. Oh. I agree. So yeah, like a slightly less than 1%, something like that. And you're like, so what? I mean, it's not going to save me from getting sunburned or something like that. But if you can detect a 0.1% drop in the overall brightness of a star, maybe you can infer something about something orbiting it. So now just think about transits as like miniature solar eclipses by some planet that isn't our own, or the moon. Okay. So that is that. I think we should stop. And questions on exercise 1, any questions on this stuff? Questions on exercise 2, or if you want to break out the solar mapping software and visualize the motions of stuff in the sky a little bit more, cast horoscopes, we can do that too. Basically take like a 20-minute break. Yeah. Yeah, that is exactly right. This is how we detect, in large part, planets around other stars. But the important part is that the two things happen proportionally. So imagine the size of the planet at this distance, the apparent size of the planet, like 50 light years away, something the size of even Jupiter. So small. But then the light from the star itself is also much less. So this 0.5%, we'll call it 0.5% drop in the total amount of light, that scales. No matter how far close you are from the star, during the transit, it's 0.5% less. And that happens if it's close and everything's big and bright, or if it happens if it's far away. So, yeah, the way that you get that accurate is all of the stuff that we'll talk about when we talk about actually observing stuff. And you need to know that you know the total amount of light coming from the star accurately to within less than that. So you need to know that you're collecting the total amount of light from the star to within like 0.1% or 1/100%. And, the atmosphere, the same thing that is, making our seasons, is really kind of horrible for actual visible astronomy. So the instrument that actually did most of the transit detections, it was in space. And that's the easy way. It's like I would call it the cheap way, but it's like the kind of foolproof way of making sure that you have really good data is you just get above the atmosphere. And then, oh yeah, absolutely, you look at a star and you can detect its total amount of light to within like 0.0001% or something. Maybe not that good. But yeah, it's hard, but the good news is they both get smaller together, both the light from the star and the blocked light from the planet. Yeah, good. Other questions? Okay. So just in case anybody wanted to know what this thing is, so this is called the analemma. And so that's the seasonal effect. So higher in the sky, lower in the sky. This slight wobbling, this is the fact that we're moving closer and farther away. So this is the elliptical effect. And in fact, the elliptical effect, I think, for us is greater in winter. So I think in the northern hemisphere, we're closer to the sun in winter. So that's nothing either. But it does produce this. So this was a picture taken at, call it like 2-week high noon intervals, counting 24-hour increments. And you see both the sun getting higher and lower in the sky, and it looks like we're going a little bit faster and a little bit slower. So the sun seems to be pushed forward and backwards. But I'll just leave that there. Okay.